Hello viewers, myself Muniraju Naidu, Assistant Professor, Department of Computer Science and Engineering, working at Institute of Aeronautical Engineering, Hyderabad. So in this video, I am going to discuss about CPU scheduling. So particularly in operating system, to concentrate on this particular scheduling algorithms, right? So this particular CPU scheduling, in the sense how processor schedules various processes. So in real-time applications, number of processes or jobs are executed. Those may be either a foreground process or a background process. So whatever the process, it is a responsibility of the processor to schedule that particular process and complete the execution of that particular process, right? So here these are the concepts related to the CPU scheduling, basic concepts, scheduling criteria and various scheduling algorithms, thread scheduling and multiple processor scheduling, and some examples related to the operating systems and algorithm evaluation. So what are the basic objectives of this CPU scheduling, right? So why we learn this particular CPU scheduling, where it can used. So to introduce CPU scheduling, that is the basis for multi-programmed operating systems, right? So nowadays we are very familiar about this multi-programmed operating systems. So particularly this particular processor scheduling, which plays a vital role in multi-programmed operating systems. Then to describe various processor scheduling algorithms. So there are certain algorithms like FCFS, SJF, round robin priority, right? So to describe various processor scheduling algorithms, and we need to discuss about what is the evaluation criteria for selecting a particular CPU scheduling algorithm for a particular system, because we have vast number of processor scheduling algorithms, right? But how can we choose for this particular application, for this particular process, so which algorithm is suited, right? So these are the basic objectives related to the CPU scheduling. Then always according to the operating system, we need to increase the throughput, right? So throughput in the sense number of jobs executed per unit time, right? So who executes that particular jobs, how we need to increase the throughput. So in the sense here we need to maximize the processor utilization, or that is only possible with multi-programming, because whatever the capacity of the processor like P7 or Intel Pentium 7 with 3.6 gigahertz. So which means that that particular processor is capable of executing up to the 3.6 megahertz. That means how many number of processors are going to be executed. That is the main aim, right? Always we need to maximize that particular processor utilization. That is obtained only with the multi-programming. Now here CPU input output burst cycle, right? So what is meant by this particular burst cycle? See, for example, if you take whenever any particular processor which is going to be executed, let us take simple example, 3 processes, right? See, for each and every process there exists some burst time. We can call it as this is the total time taken to execute this particular process. So always these are in the milliseconds, right? See, which means that process P1, the total execution time for that particular process P1 is 10 milliseconds. Similarly, for process P2, 7 milliseconds. Process P3, 50 milliseconds. Right? So, once the processor can access this particular process for execution purpose, then it takes 10 milliseconds to execute this particular process. Right? So, that is here we can call it as a CPU burst cycle. So what is the IO burst cycle? If this particular process is waiting for some event, or it changes its states from running state to the waiting state, Waiting state is nothing but here each and every process must wait for certain event, right? So that is how much time it is waited. That depends upon the interrupt occurs. After that, again it starts the execution. So here the process execution, which consists of a cycle of CPU execution and input output wait, right? So what is the total time for CPU execution? That is the 10 milliseconds. If for example this particular process P1, which is waiting up to 20 milliseconds in the ready queue, right? So the total time is here it takes to execute this particular process 10 plus 20, 30 milliseconds, right? So without interrupt, directly processor can accept this particular process. It takes only 10 milliseconds. So here the CPU IO burst cycle, which represents the process execution, which consists of cycle of CPU execution and input output wait. Then here we can concentrate on the CPU burst distribution. How this particular 10 milliseconds is distributed. So depends upon the some algorithms like preemptive scheduling algorithms, right? So this particular 10 milliseconds is divided, and each and every individual time that particular processor can accept this particular process and for the execution. See, this is the alternating sequence of processor and input output burst. See here, this is a load and add some instructions. Load, store, add, store, read from the file. So which is here we can call it as a CPU burst. CPU burst. So it is executed, right? Some instructions are executed within that particular process. If the particular process is entered into the preemptive state, in the sense it's wait for any input output, then automatically the processor execution stops here and it enters into the state we can call as a input output burst. After some particular period of time, then again some more instructions are executed, like a store, increment, index, write to a file. So then CPU burst. So like this, CPU burst, IO burst, CPU burst, IO burst, right? So this is we can call as an alternating sequence of processor and IO burst. Then coming to this our concept, that is a CPU scheduler. CPU scheduler. So here the processor which schedules various processes, or we can call it as a jobs or tasks, right? Now the question is how the processor selects various jobs and where that particular processor keeps that particular jobs, right? See, basically we have certain categories of queues, right? So we need to describe here like ready queue, waiting queue, device queue, like that, right? So first of all, processor selects from among the processors in ready queue, right? So whatever the processors which are waiting at the ready queue, like P1, P2, P3, P4. So these are all the processors entered into the ready queue. Now the processor selects among these processors like P1, P2, P3, P4 and allocates that particular processor to that particular process, right? So here the queue may be ordered in a number of ways, like ready queue, waiting queue, as well as the device queue. Now CPU scheduling decisions takes place whenever a process switches from running state to waiting state, right? So basically we have 5-state process model, right? So the states are new, ready, running, waiting, terminated, right? So these are the 5 states: new, ready, running, waiting, and terminated, right? So here the CPU scheduling decisions may takes place whenever a process switches from running state to waiting state and switches from running state to ready state, switches from waiting state to ready state, then finally it terminates, right? See, these 2 conditions, like these 4 conditions are categorized into the two types basically, right? See, whenever any process which switches from running state to waiting state, as well as it terminates. So this is the scenario here we can call it as those are non-preemptive scheduling algorithms. Whenever a process switches from running state to waiting state, right? So that means whenever any particular process is executed for particular event, right, it switches from that particular running state to waiting state, or simply it is a terminates. That is, we can call it a non-preemptive. Non-preemptive in the sense, right, whenever the processor accepts any particular process, that particular process is completes its execution, then only the processor can accept the next process. Simple. Next criteria, whenever any particular process switches from running state to ready state, and switches from waiting state to ready state. So this is here we can call it as a preemptive scheduling algorithms. So we know what I mean by preemptive. See here, consider access to shared data and consider preemption while in the kernel mode. So we will discuss later what is a kernel mode and what is a user mode. Then consider interrupts occurring during a crucial operating system activities. See, definitely whenever any particular processor accepts the process and it enters into the running state, based upon some interrupts, definitely the particular processor preempts the process and accepts the interrupt. So that depends upon the priority, right? So simply preemptive means each and every process may execute sometime and again it entered into the waiting state. And whenever the processor can accept this particular process, again it activates and it executes the remaining time. So that is here we can call as a preemptive scheduling algorithms. So like this scheduler, CPU scheduler, we have dispatcher, right? So this particular dispatcher module gives control of the processor to the process which is selected by the short-term scheduler. See, basically we have schedulers like long-term scheduler, medium-term scheduler, and short-term scheduler, right? See, the dispatcher module which gives control of the processor to the process which is selected by the short-term scheduler. So this particular short-term scheduler which consists of switching context. So you know what I mean by switching context of each and every process, right? So you know we have a PCB, process control block. Within that process control block, in addition to the process ID, process name, we have process context. So that is here the switching context. So where the particular processor stops the execution of a particular process, and again whenever the particular processor accepts the process for execution, the next we can call it as already the processor accepts one particular process like P1, right? So the total time, execution time for that one is 10 milliseconds. Well, what happened initially, the process P1 which is executed by the processor, it executes only 3 milliseconds. What about remaining 7 milliseconds? After some particular period of time, now the processor can accept the same process P1 and it starts execution from 4th millisecond, not from the 1st millisecond. So it starts execution from the 4th millisecond. So that is here we can call it as a switching context. Then switching to user mode. So we have kernel mode as well as the user mode. Then jumping to the proper location in the user program to restart that particular program. So this is the purpose of the dispatcher. So what I mean by dispatcher? Latency. So the total amount of time it takes for a dispatcher to stop one process and start another process in the running state, right? So that is very minute time, right? So that particular time here we can call as the dispatch latency. See, scheduling criteria. So this is Very important rather than defining or discussing the various scheduling algorithms. Definitely, you should know about scheduling criteria, right? So, what is a scheduling criteria? Right? Whenever any particular processor can accept some set of processes and those processes are for execution purpose, then definitely whatever the algorithm we are using, that particular algorithm must use these particular scheduling criteria. What are those? First one is processor utilization, CPU utilization. That means keep the processor as busy as possible. That means always the processor needs to execute any one of the process, either that is the background process or that is the foreground process. Then throughput. Throughput in the sense number of processes which complete their execution per unit time. Right? So the total number of jobs executed per unit time by the processor. That is the throughput. Then turnaround time. Turnaround time. So the amount of time to execute a particular process which is called as a turnaround time. Right? So for each and every process there exists some turnaround time. So based on that particular turnaround time, the processor allocates some speed and it executes that particular process. Then waiting time. Waiting time. Amount of time a process has been waiting in the ready queue, not in the job queue. It is in the ready queue only. That is here we can call as a waiting time. Amount of time a process has been waiting in the ready queue. Sorry. Next, response time. Response time. Right. See here, in case of operating system, each and every resources may be utilized by the processor in the sequence request, use, release. Request, use, release. See, first of all, whenever I need to access Google server, right, automatically I need to open Google from my laptop. Now what happens here, my particular system creates one particular process. That particular process here, Google Chrome, right, or opens that particular Google Chrome. Now what happens, whenever I need to search for something in the Google, then automatically according to the processor, this is the process which may send some request to the Google server. Is it right? If that particular time, at that particular moment, if the Google server is free, then it allocates to that particular process. If it is not free, then automatically it takes some time. So, after completion of our work, finally we need to release that particular connection. We need to release that particular connection. Right? So, is a way we can call as a request. If it is allocated, use. After completion of your work, simply we need to release that particular connection. So, response time, amount of time it takes when a request was submitted until the first response is produced. Right? See, if you take another simple example, whenever you can surf the web through any particular internet cave, there what happens, very limited bandwidth, there is bandwidth which is allocated to the some n number of systems. Right? See, whenever just you need to start, we can call as a just open www.iare.ac.in. Right? So, how much time it takes that particular system, whatever the system which is available in the internet cave, right? So, how much time it takes to open that particular IARE web page, right? So, that means within certain point of time, very limited time, whether the particular page is opened or it displays some message, right? Our network is slow, right? Or something. So, that means here we can call as a response time. How much time it takes to open that particular page. That means according to the user, according to the system, user sends some request to that particular server. If it is free, automatically it allocates to that particular user. Right? So, we can call as a amount of time it takes from when a request was submitted until the first response is produced. That first response may not be the output, definitely. Right? So, whatever the response, that is we can receive, that is we can call it as a response time. So particularly this response time is very important for time sharing environment, right? Then coming to this scheduling algorithm optimization criteria. Scheduling algorithms optimization criteria. See, here we have maximize the processor utilization and maximize the throughput, right? So because maximum CPU utilization means more number of jobs are executed. Maximum throughput means so not even a single second processor is in an idle state. Always the processor is busy to execute some process or jobs. Then similarly, scheduling algorithm optimization criteria, the next level is, you can call it second level, minimum turnaround time, minimum waiting time and minimum response time. So, see here. This is your scheduling criteria. See here. CPU utilization, throughput, turnaround time, waiting time as well as the response time. Right? See here. CPU utilization, throughput, waiting time, response time, turnaround time. But the first two definitely must be in the max. We can call it as a maximum CPU utilization and maximum throughput. Similarly, minimum turnaround time, minimum waiting time and minimum response time. So these are the scheduling algorithms optimization criteria. Now coming to this scheduling algorithms, scheduling algorithms. So we have FCFS, first come first serve scheduling algorithm, and SJF, shortest job first, and priority scheduling algorithm, and RR, round robin scheduling algorithm, and MQ, multi-level queue scheduling algorithm, and multi-level feedback queue scheduling algorithm. Right, so there are a number of algorithms, right? So thread scheduling, multiprocessor scheduling, multi-core scheduling, right? See, coming to this first one, FCFS, first come, first serve. So the name itself, it specifies that first come, first served. So that means whatever the process which comes earlier, automatically the processor accepts that particular process and it executes that particular process, right? So that is, we can call it as a FCFS scheduling. So what is meant by scheduling? Basically, how the processor executes number of processes among the existing processes, right? Which process executes at what time and another process executes at what time, right? So this will look after the processor. So here we need to describe that FCFS scheduling algorithm, right? See, for example, let us take a simple example to explain this algorithm. The process P1, process P2, process P3. We have three processes. So the burst time for this particular process P1 is 24 milliseconds. So here that is milliseconds. Then process P2, 3 milliseconds, process P3, 3 milliseconds, right? Fine. So these are all the, burst times. Burst time is nothing but the total execution time of that particular process, right? For P1, it takes 24 milliseconds. For P2, it takes 3 milliseconds. And for P3, it takes 3 milliseconds. Suppose that the processes arrive in the order like P1, P2, P3. This is very important because, in case of FCFS scheduling algorithm, always the processor can execute the process in the order in which they arrived into the system. So for that here, suppose that the processes arrive in the order P1, P2, P3, right? So according to the algorithm, what it says that, see, at 0th millisecond, the processor starts execution. So who is the first process to enter into the ready queue? P1. So P1. How much time it takes to execute? 24 milliseconds. So 0 to 24 milliseconds. Now P1 is executed. Then the next process P2. P2 will arrive. So automatically the processor schedules that particular process because on first come first serve basis P2. So how much time it takes to execute that particular process? 3 milliseconds, right? So according to the processor, from where it stops execution of the previous process, that is here. Here that is 24 at 24 millisecond. And from that particular point of time, it takes these many number of milliseconds of time to execute the associated process like P2. So the P2 it takes 3 milliseconds. See, this is the 3 milliseconds. But we need to always calculate from the starting point. So it takes 0 plus 24 plus 3, 27 milliseconds. Then P3, the process P3. So the burst time of process P3 is 3 milliseconds. So here, from here to here, the 3 milliseconds, the processor which executes the process 3. But according to the starting, 27 plus 3, 30. Now here we need to calculate the average waiting time. Average waiting time. So we know what is the waiting time for each and every process. See, initially there is no waiting time, right? Because on first come first serve basis, initially the process P1 entered into the queue, so automatically the processor executes that particular process. So the waiting time for P1 is 0 millisecond. Then at what time the processor catches the process 2? How much time the process P2 will wait? So that is here the waiting time for process P2, 24 milliseconds. Similarly, for process P3, it takes 27 milliseconds to execute the process T. See, one important point here, rather than its burst times, because P2 and P3 is having very less time when compared to the P1, that is the 24 milliseconds. So rather than its burst times, here the FCFS scheduling algorithm activates, or else you can call as execute the processes in which order they arrived into the queue. So here the P3, 3 milliseconds. So the P3 waiting time is up to 27 milliseconds. The process P3 is waiting, right? After 27 milliseconds, the processor can access that particular process 3. So here 27 milliseconds. Now we need to calculate the average waiting time of the 3 processes. We know average waiting time for process P1 is 0 and average waiting time for process P2 is 24. Average waiting for process P3 is 27. You know, we need to find the average total number of processes divided by the total number of processes. So that is the 27 plus 24 plus 0 divided by 3. 51 divided by 3. That is the 17 milliseconds. Here, the average waiting time for this particular process are 17 milliseconds if the processes arrive in the order P1, P2, P3. See what happens if the process arrives in different order like P2, P3, P1, P2, P3, P1. Then this is we can call as a Gantt chart. Gantt chart. So this is very important in scheduling algorithms. So the Gantt chart for this particular schedule, right? So first one is P2. So 0 and P2. You know what is the burst time for P2? 3 milliseconds. Then again the next one is P3. For P3 also it takes 3 milliseconds. Now for P1 it takes 24 milliseconds. Right? Fine. But see here, for P2 at starting point 0, how much time? 3 milliseconds. So here 3. And for P3, again it takes 3 milliseconds. But according to from starting to here, 3 plus 3, 6. And for P1, actually the burst time is 24. 24 plus waiting time is 6 plus 3. That is the 6 plus 24. That is the 30. So the waiting time for P1 is 6. The waiting time for P1 is 6. waiting time for P2 is 0, waiting time for P3 is 3. So simple, waiting time for each and every process, simply we need to identify the number which is left hand side. Similarly, what is the turnaround time of that particular process, we need to represent with the right hand side. So the average waiting time 6 plus 0 plus 3 divided by 3, that is a 3 milliseconds. See, previously we have 17 milliseconds if the processes P1, P2, P3 in that particular order. Now we have 3 milliseconds if the processes are P2, P3, P1. So that means this is the much better than the previous case. So in case of FCFS, we have convoy effect. So that is the short processes behind the long processes, which means that, see here, P2, P3 is having the 24 milliseconds, sorry, 3 milliseconds, very less burst time when compared to the P1, because P1 is having the 24 milliseconds. Rather than the order, right, definitely P1, P2, P3 means the processor can execute process P1. That means total 24 seconds is 24 milliseconds are executed, then only the processor can catch up the second process. So that is here we can call it as a convoy effect. Consider one CPU bound and one mini input output bound processors. So this describes about our FCFS scheduling algorithm. Now, based upon this particular concept, here we need to mention that what are the advantages and what are the disadvantages. So definitely for each and every algorithm, there is a number of there are number of pros and cons, right? So advantages. First, this is a very basic algorithm to define these scheduling algorithms. So it is very simple to understand. So what is the concept here? So whatever the order in which they arrived into the queue, the processor can accept those process and completes its execution. Finally, we need to calculate the average waiting time. So what are the drawbacks here? See, the process with less execution time which suffers, like in our previous example, P2, P3, which is having very 3 milliseconds less time when compared to the P1. P1 is having the 24 milliseconds. So the process with less execution time will suffer. That is, waiting time is often quite long, right? Then it favors the CPU bound process, then input output bound process. So definitely it favors the CPU bound process, because let us take the previous example. Here the first process will get the CPU first. Definitely. So the first process is P1, which takes 24 milliseconds. So what happens? Other process can get the processor only after the current process has finished its execution. That is, 24 milliseconds are completely executed, then only the processor can handle the second one. Now suppose the first process has large burst time and other process have very less burst time. So for our understanding purpose here, we can take the standard example like 24, 3 and 3. But whereas in case of real time, it takes so much of time, like 10,000 milliseconds, 2,000 milliseconds, so like that. So that is here we can call as a convoy effect. Convoy effect, right? So when compared to the remaining algorithms, based upon this convoy effect, this particular effect results in the lower CPU and device utilization. So according to this FCFS scheduling algorithm, the processor utilization as well as the device utilization is also less, right? So particularly this algorithm, that is FCFS, is particularly a troublesome for time sharing systems, because there we need to concentrate much on how that particular processor at regular intervals of time that shares that particular processor to all the processors. So that deals about the disadvantages of FCFS. Then coming to the next one, SJF, shortest job first. Shortest job first. See, shortest job first, which means that whatever the process, so let us take our simple example, 24, 3 and 5. So this particular algorithm, according to this particular algorithm, how the processor executes the processes means, first of all, whatever the process which is having the less burst time, we can call it as a shortest job first, right? So for example, here This is the length of this particular P2, that is the 3. So the processor can handle this particular process initially. Now, when compared to the remaining 2, which is having the less time. So, second time, the processor can accept this particular process. So, P2 first, P3 first, then P1. Right? So, this particular shortest job scheduling algorithm, which associates with each and every process based upon the length of its next CPU burst. Based upon the length of its next CPU burst. So, use these lengths to schedule the process with the shortest time. So, based upon these 3, which one is having the shortest time? That is the first process enters into the queue for execution purpose. So, here SJF is optimal when compared to the FCFS algorithm. Shortest job first is optimal because it gives the minimum average waiting time for a given set of processes. Minimum average waiting time for a given set of processes. But what is the drawback in this SJF? See, the difficulty is knowing the length of the next CPU. Right? So, this is very simple example. Let us take any real-time example. There we can't find exactly what is the length of the next CPU request. Right? So, that is happens in this particular SJF. So, this is the example for SJF scheduling algorithm. See, let us take 4 processes P1, P2, P3, P4. So, the host time for the associated processes are P1 6, P2 8, P3 7 and P4 3. Now, here we need to explain this particular SJF scheduling algorithm based on these 4 processes and the associated burst times. Right? So, first of all, we need to draw a Gantt chart. See here 0, right? Among those 6, 8, 7, 3. Among those, which process is having the shortest job? That particular process first entered into the ready queue. See, tell me here, this is the first one, right? So, because 3. Then, the second one is P1 because 6 milliseconds. Then, this is 3, this is 4. See here, P4 starting and what is the total time takes to execute? 3 milliseconds. So, P4 3 milliseconds. Right. So, after 3 milliseconds, who is waiting at the ready queue? Like P1 because it is having the 6 milliseconds burst time. So, P1. So, from here, it takes 6. So, 3 plus 6, 9. Then, the next category is P3 because it's having the less CPU burst time when compared to the P2. So, P3. What is the P3 burst time? 7 milliseconds. 7 milliseconds. So, 7 plus 9, 16. Finally, P2, 8 milliseconds. 8 plus 16, 24. So, in this way, the SJF scheduling algorithm will work. So, here we know how to calculate the average waiting time. Waiting time of P1 is 3, P2 is 16, P3 is 9, P4 is 0 divided by 4 that equals to the 7. So, this is version here we can call it as a preemptive version. In another way of call this particular SJF scheduling algorithm is shortest remaining time first, SRTF. Shortest remaining time first. So, that is the preemptive version of SJF scheduling algorithm. Right. See here, SRTF. In addition to that, process and the associated burst time, here we add the concept of varying arrival times and preemption to be analysis. Varying arrival times and preemption to be analysis. Right. See, P1, P2, P3, P4, the burst times for P1, P2, P3, P4 is 8495. 8495 milliseconds. But whereas the arrival time for this particular process is, for P1, it starts at 0 and P2, it takes 1 minute to arrive and P3, 3 and P4, 3. Now, we need to prepare the Gantt chart regarding this particular SRTF. So the preemptive SJF Gantt chart is, see here, initially the process P1. Initially the process P1 entered into the queue, right? After 1 millisecond, process P2 entered into the queue. See, that is P2. After 1 millisecond, P2 will enter into the queue, right? But what happens here? P2 burst time is 4. P2 burst time is 4. So within that particular 4, already 1 millisecond is executed, right? So which one is executed? P2. So P2, it takes 4 milliseconds, right? So each and every time the processor compares its burst time, because the algorithm specifies that shortest remaining time first. Shortest remaining time first. So initially P1. So 1 millisecond is executed, which means that 8 minus 1, because 1 millisecond is already executed, 7. Next P2. P2 arrival time is 1 millisecond. So the total time it takes to execute the process P2 is 4 milliseconds. 4 milliseconds. So it executed. So that means, see here, P2 4 milliseconds. Yeah. But from starting point, 1 plus 4, 5 milliseconds. Right? So that is P2 is successfully executed. Now coming to this, we have 7, 0, 9, 5. So which one is the shortest among these 7, 9, 5? 5 is the shortest. So the associated process is P4. So P4 is executed, right? For P4, it takes 5 milliseconds. 5 plus 5, 10. So here, this is the also executed. Now, the processor compares the 7 and 9. 7 and 9. So for P1, it takes 7 milliseconds, and for P3, it takes 9 milliseconds. So this is the shortest. So P1 is started execution. So that is the 7 milliseconds, right? But 10 plus 7, 17. So now at the second level, this is also completed. Now only the process which is left behind, that is the only process P3. So 9 milliseconds. So this is 9 milliseconds. 9 plus 17, 26. We know how to find the average waiting time. Average waiting time of preemptive scheduling algorithms. See here, simple example. The process P1, the waiting time is here 10. But already process P1 is executed previously up to 1 millisecond. So the average waiting time, whenever we need to calculate, simple follow this particular rule. So 10 minus 1 plus 1 minus 1 plus 1 minus 1. So this is related to the process P1, right? Yeah, process P1 and process P2. Then process P3. Process P3. So it takes 17 milliseconds to reach that particular process P3. At the same time, the arrival time of process P3 is 2 milliseconds. So 17 minus 2. So this is the process P3 waiting time. Then process P4. 5 minus 3. See here, this is the process P4. So the total divided by 4, that's 26 by 4, 6.5 millisecond. So this is the preemptive SJF Gantt chart. So what are the advantages and what are the disadvantages of this particular shortest job first when compared to the previous algorithm? So first of all here, the shortest jobs are favored because we know already in FCFS, P2, P3 burst times are 3 milliseconds, whereas P1 burst time is 24 milliseconds. But P1 is just arrived in front of P2 and P3, so automatically the processor can accept and we can call it execute the process P1 only because the arriving order is P1, P2, P3. What happens here? In case of SJF, each and every time the processor rechecks the the burst times. Based on that, which one is having the less burst time to execute that particular process initially. So the basic advantage is shortest jobs are favored when compared to the remaining algorithms, and it is probably optimal in that it gives the minimum average waiting time for a given set of processes. So these are the advantages. See, definitely any algorithm we have some drawbacks, right? Based on the particular drawbacks, we need to improve the next algorithms. So what is the disadvantage of SJF scheduling algorithm? SJF may cause starvation. So this is very important. SJF may cause starvation. So what do you mean by starvation? If any particular process is having the less burst time, that particular process is waiting for a long period of time, right? So that is the starvation. So what is the solution for this particular starvation? That is the aging. So what happens? What is meant by aging actually? Just we need to improve the priority, right? Or improve the level of that particular process, and at one particular point of time, the processor can accept that particular process and go for the execution. So it cannot be implemented at the level of short-term CPU scheduling. So this particular aging, and we can call it as a starvation problems, which is solved by the aging. But this particular SJF scheduling algorithm cannot be implemented at the level of short-term CPU scheduling algorithms. Right? The deals about the SJF scheduling algorithm. Then third one, priority scheduling. Third algorithm is priority scheduling. So we know what is meant by priority. What is meant by priority? So generally, in real time, we have a normal guy and important guy and very important guy, VVIP, something, right? So definitely we can give some priority to someone. That depends upon the condition, or depends upon the process. Like according to the operating system, we have system processes as well as the application processes. See, definitely the system can give some importance to the system process only, because without any system process, the application process may not be run, right? So a priority, which is an integer that is associated with each and every process, right? So until in case of FCFS, just we need to mention the P1, P2, P3 and burst times P1, P1 24, P2 3 and P3 3 milliseconds. Whereas in case of SJF, shortest job first, rather than providing this particular things in case of SJF, right? We need to mention that arrival times. In addition to those, here in case of priority, we need to assign one particular integer, like just like ranks, right? So this particular student roll number, which is having the which rank, first rank, second rank, third rank. So that is the highest priority. We can use a lowest integer number. So here the processes is allocated to the process with the highest priority, right? Please be understood. Here, the processor can allocate the process with the highest priority. Highest priority in the sense, whatever the process which is having the smallest integer, that is having the highest priority. Just like MSET top 1, top 2, first rank, second rank, third rank. So first rank is having always high priority when compared to the remaining all. But this particular priority scheduling algorithm classified into preemptive scheduling and non-preemptive scheduling. We know difference between preemptive scheduling and non-preemptive scheduling, right? So preemptive scheduling. So each and every process executes some portion of its burst time, and again it entered into the waiting state. Right. So after some time, whenever the processor fetches that, again it go for the execution. That is the preemptive. Non-preemptive means once the processor handles, then it executes fully and then it catches the next process. So SJF is priority scheduling, where priority is the inverse of predicted next CPU burst time. So that is a drawback existing in the previous algorithm like SJF, right? We can't say what is the next process and how much time it takes to execute, because in real-time applications also is not possible. But SJF is priority scheduling, where priority is the inverse of predicted next CPU burst time, right? So what is the problems existing? There is a starvation. Right? So that particular starvation problem You know what is meant by starvation? Always the low priority processes may never execute. Low priority processes may never execute. So they're still waiting in the ready queue only. So what is the solution for that particular starvation? The solution is we can call as a aging. Solution is a aging. What do you mean by aging? So as time is progresses, we need to increase the priority of the process. Right? After some time, whatever the process which sits under the 10th priority, just we need to keep that particular process in the 9th priority, then 8th priority. So like that, after some particular point of time, that particular process having a chance to enter into the first priority level, so automatically the processor can catch up and execute that particular process. So this is a priority scheduling, basically priority scheduling. So this is the example. With the help of this particular example, I need to explain clearly this particular priority scheduling. See here, processes, we have 5 processes, P1, P2, P3, P4 and P5. The burst times of each and every process, that is in milliseconds, P1 10, P2 1, P3 2, P4 1 and P5 is 5. The priority, the associated level of priority is, see here, so that means which is having the highest priority, right? So irrespective of this particular burst times, here we need to concentrate on the priority, right? So what is the first priority process? P2. See P2 at starting 0. This is the first priority process, enters into the queue. What is the total execution time? 1 millisecond. See, this is the 1 millisecond. At this particular point of time, P2 is executed. So we have P2 is executed. Then what is the next priority? P5. Because priority level is 2. So P5. P5. What is the burst time of P5? Here 5 milliseconds. So it takes 5 milliseconds. Already from starting point 5 plus 1, 6. So P5 is also executed. Then the priority level is P1. The third priority is for the P1. So P1. How much time it takes to completely execute? 10 milliseconds. So it takes 10 milliseconds. 10 plus 6, 16. So P3 is also, P1 is also completed. Then fourth priority level, that is the P3. It takes 2 milliseconds. So P3, it takes 2 milliseconds, 16 plus 2, 18 milliseconds. Right. So P3 is also completed. Now last remaining one is P4. P4, that is the last priority. That is the fifth priority. How much time? The total execution time, that is a 1 millisecond. So it is 1 millisecond. 18 plus 1, 19. Is it right? So this is, we can call as a priority scheduling algorithm. Right? So now we need to calculate the average waiting time. So we know how to calculate the average waiting time. So first of all, waiting time of P1. You know from the Gantt chart, waiting time of P1 is 6. Waiting time of P1 is 6 and waiting time of P2 is 0. Waiting time of P3 is 16. So already I explained that waiting time here we need to follow the simple thumb rule, like whatever the number which is associated in the left side of the particular process, that is we can call as a waiting time, right? And for P4 18 and P5 1, right? So divided by total number of process 5. So here we can get the 8.2 milliseconds. So this is the simple example. Here we need to clearly explain about the priority scheduling algorithm. So what are the pros and cons of this particular priority scheduling algorithm? Right. The first advantage is this particular priority scheduling algorithm provides a good mechanism where the relative importance of each and every process may be precisely defined. Right. So already clearly defined that. So this is the process which is having this particular priority. This is the process which is having this particular priority. Right. So that is very good, because each and every process which knows what is the level of that particular process. But what is the drawback? If high priority process use up a lot of CPU time, then automatically the lower priority process may starve and be postponed indefinitely. Because, right, if the first process which is having the highest priority, but the particular process, the total execution time of that particular process is, let us take 100 milliseconds. Then what happened? Second process, which is having the second priority level, which is having only 2 milliseconds, right? So rather than the priority here, whatever the previous level of any particular process, right? So which is used a lot of CPU time, then always the next level of processors may starve and can be postponed indefinitely. So this is a situation where a process never gets scheduled to run, which is called as a starvation. And another one, in real-time applications, another problem is to decide which process gets which priority level assigned to it. Okay, because at one particular point of time, for example, n number of processes are there in my system. So within that particular n number of processes, here we need to easily identify that, like P1, P2, P3 and so on up to the Pn. So here we can mention the priority also. So this is the, we can call as a P1. So this is the first priority level, this is the third priority, second priority, this is the third priority and so on. This is the nth priority level at one particular point of time. Slowly my processor is executing some set of processes like P1 and P2. After that my system can accept n plus m number of processes. Then automatically the priority levels are also changed. There is a problem in deciding which process gets which priority level assigned to it. So that is a drawback existing in the priority scheduling algorithm. Next one, round robin scheduling algorithm. Round robin scheduling algorithm. So the name itself specifies that round robin, in the sense here the processor can accept each and every process in a sequential, that is, you can call it circular fashion. So whatever the processes which comes under the execution, so those processes are simply arranged in a circular fashion, right? Let us take simple example, right? So now the processor can accept one particular process for execution time, but the algorithm which specifies that one terminology, we can call it as a CPU time. That is, how much time the CPU engages the process, that particular process. How much time the CPU engages the next process. For this, here whatever the CPU time here we can call as it, that is the time quantum. Here the time quantum is fixed for all the processes, irrespective of their burst times, right? So each and every process gets a smallest unit, that is we can call as a time quantum, that usually between 10 to 100 milliseconds. Once that particular time quantum is elapsed, then automatically the process is preempted and added to the end of the ready queue. Let us take a simple example. If there are n processes in the ready queue, and the time quantum is a small q, this is the time quantum, then each and every process gets 1 by n of the CPU time. CPU time lo 1 by n of the CPU time ustadi, right? So that is, no process waits more than n minus 1 into q time. No process can wait more than n minus 1 into q. So here the timer interrupts every quantum to schedule the next process. See here, P1, P2, P3, P4, P5. So P1 executes first, P2, P3, P4, P5. Again P1. So this is in a circular fashion. So here a round robin scheduling algorithm which is executed based upon the time quantum. So let us take a simple example to clearly explain about this round robin scheduling algorithm. See here the time quantum is 4 milliseconds. That means how much time the processor engaged, process P1 to process P2, only 4 milliseconds. Now let us take a same example which we consider for FCFS also. P1, P2, P3, 24, 3 and 3 milliseconds. Right? So what the concept related to this round robin scheduling algorithm, you know, each and every process irrespective of its burst time, right, it executes only 4 milliseconds, up to the 4 milliseconds, because here the time quantum is fixed. So initially the process P1 So 0 process P1. How many milliseconds the process P1 is executed? 4. So 24 minus 4. That is remaining time. Here I am writing remaining time. Right? So 20. So P1 is executed for first 4 milliseconds. Now the processor enters to the next process, that is the process P2. The total burst time for process P2 is 3 milliseconds. See, this particular burst time is less than or equal to the time quantum. Then the particular process is not preempted, is successfully executed. See, P2, here it takes 3 milliseconds. Right? So it takes after 3 milliseconds, the processor can accept the next process, that is the P3. So 3 means already 0 plus 4 plus 3, 7. So P2 is executed successfully. So then no need to discuss about this particular P2. Then the processor chooses the process P3. How much time? 3. Now we compare that this particular burst time is less than or equal to the time quantum. 3 is less than or equal to the 4. So P3 is executed. P3 is also executed. So 3, 7 plus 3, 10. Completed. Now the processor checks that any other process is there. If so, then automatically the processor which handles the process P1. So what is the remaining time existing in the P1? Previously 20. But what is the time quantum here? 4. So again the processor from P3 to the processor directly handles the process P1. So only 4 milliseconds are executed. So see here, only 4 milliseconds. After that, again the process P1 is preempted. So that is 16. Again 4. See here, again 4. So 12. Again 4. 4. So like this until it reaches to the 0. Here the processor can handle that particular process based upon the time quantum. So based upon this, we need to easily calculate the average waiting time. So typically higher average turnaround time than our previous algorithms like SJF, but better response time, because here the time quantum should be large when compared to the context switch time. Right? So depends upon the application, this particular time quantum usually maybe either 10 milliseconds to the 100 milliseconds. But whereas context switch is always less than 10 seconds. What are the advantages and disadvantages of this algorithm, that is round robin scheduling algorithm? First advantage is every process gets an equal share of the processor. Right? So like this, see here already we explained that each and every process can get the equal share of the processor. Right? Whatever the burst time, the processor based upon the time quantum, it executes 4 milliseconds. Again, it executes next 4 milliseconds of the next process. So like this round robin scheduling algorithm is a cyclic in nature. So there is no starvation. So that's why here I need to mention this particular pictorial representation like a circular fashion. So round robin is a cyclic in nature, so there is no starvation. But what are the drawbacks, disadvantages? Setting the quantum too short, then automatically it increases the overhead and lowers the CPU efficiency. See, rather than putting this particular, you can call it the time quantum 4 milliseconds, just we need to mention that time quantum as 1 milliseconds. What happens? Each and every time the processor picks each and every process. P1 1 millisecond, P2 1 millisecond, P3 1 millisecond, again P1 1 millisecond. So like this, which increases the overhead and lowers the CPU efficiency. But setting it too long may cause a poor response time to the short process. Right? So that means the time quantum is also not 20 milliseconds, 30 milliseconds. Right? So, but setting that too long may cause poor response to short processes. So, average waiting time under this round robin scheduling algorithm is often quite long when compared to the remaining algorithms. But only one advantage is here, each and every process can get the equal share of the CPU. So there is no starvation in this particular, by using this particular round robin scheduling algorithm. Right? So thank you. So in this video, I'm explained you like scheduling algorithms. So what is meant by scheduling and what are the scheduling criteria and different types of scheduling algorithms, scheduling and scheduling criteria, and scheduling algorithms like FCFS, SJF, priority, and round robin. So, in this video, I discussed these concepts starting from process scheduling, what is meant by scheduling, what are the objectives, and what is meant by scheduling criteria, and what are the various scheduling algorithms. Among those, FCFS, SJF, priority, and round robin. Right. So in the next video, I'm going to discuss about remaining scheduling algorithms like multi-level queue and multi-level feedback queue and thread scheduling algorithms. Right. So I hope you understood. Thank you, one and all.
Like, share and subscribe. Hit the bell icon for more updates.